solution or the suspension is going to contain the particles in it, if it is going to, if the particles are going to agglomerate more and more, so they are going to immediately settle down over here. That is called as the primary minimum. So this is like a kind of well where they're going to get dumped there, and whatever the devices that you're going to be using for them to get redispersed, they are not going to be there. They are not going to get dispersed evenly. Rather, they will always settle down. So why they should at first place settle down? It's again because of the surface charges, surface charge which is present on a particular nanoparticle with respect to the base fluid. So whenever a particle comes into contact with the water, let's say water as a base fluid, and being a high dielectric medium, so the water which contains a lot of minerals in it, and essentially water, since it has got a high dielectric constant, that means it will have more cations. That means they are positively charged ions. And on the other side, the particle which is dispersed into the water body, so the particle will have by default will actually have a negative charge on the surface, so that's called the anion. So when these cations and anions, when they come into interaction at the surface, let's say when the particle gets into the base medium, when the molecules of the base medium comes in contact with the surface of the particle, so due to the charge transfer or attraction of the negative ions and the positive ions, so you'll see that a layer which is getting formed over the particle. That layer is called as the static layer. And since the static layer or the anions which are there on the surface of the particle, they are not actually in a better position to compromise, or they are not in a better position to satisfy or neutralize the cations present in the water molecule. So what will happen is that there will be one more layer which will be formed around the static layer. That's called actually the dielectric layer, or sorry, the double layer. So between the primary external layer, static layer, and the second double layer, so you will have some kind of potential difference. And if you are able to move the ions from the double layer, so you will be able to create some kind of potential difference between the first layer and the second layer. And with that potential difference, you will be able to measure how many number of particles are there in the particular solution. So this is the basic intention with which the zeta potential analysis have been put into place. So the particles, let's say if you have synthesized a nanoparticle and if you have dispersed it into the base medium, and if you test the zeta potential of the nanofluid, if it shows like minus 25 or minus 30, then it means that yes, your particle is going to be stable, it's going to stay there for long. And if it is having a surfactant which is going to actually create a resistive barrier between one particle and another particle, like once the van der Waals forces of attraction are overcome by this steric effect, so we are going to actually have these two particles separated from each other, and they are not going to get collided. I mean, they are not going to get attached to each other. So this is going to actually make the particles stay there for long period of time. So, and there is one more thing, like primary maximum, where this is the place where I have told like the maximum repulsion between the particles are going to be pronounced, and the secondary minimum is the place where you will have a compromise in terms of the attraction and the repulsive forces. Like some particles, these particles will try to flocculate, and then they will try to settle down, but when you actually ultrasonicate them or through agitation, if you do it, they will be again able to disperse well in the solution. So if you look at some pharmaceutical applications like injections and other things, like particles, sometimes they may be there, but we won't be able to see them through naked eye, but still when you just shake it, or like syrup and all, so when you just do it, so these particles they'll get dispersed, and they does the job very effectively. And now going into the aspects which are influencing the thermal conductivity of the nanofluids. So these are the major things which we need to consider when we actually add the nanoparticles into the base fluid, like size and the shape and the concentration, aggregation, and the pH value of the solution, and also the temperature and the sonication procedure. So size, like yes, is there anything on the size that matters? Yes, it matters. Size does matter because the controlling of the size plays a vital role in terms of creating the surface charges, and the surface atoms will have more energy, or they will participate very effectively at nanoscale level when compared to the macro or micro scale levels. And the shape also has a large influence in terms of the specific surface area being developed on the particle, or let's say if it's carbon nanotube, so you will have a higher specific surface area. And again, the shape does matter a lot in terms of dispersing these particles or the nanotubes into the basic fluid. And there are pros and cons with respect to the aggregation of the particles as per the DLVO theory. So if you want to aggregate the particle in the base fluid, you will actually have a better enhancement in the thermal conductivity, because they are connected. These particles are having a very good network of the thermal interfaces, because one particle will have the contact with the other particle, and as we call by the name thermal conductivity. So conduction means you should have solid interface, and through the conduction, through the phonon interaction, you will be able to see that the heat transfer enhancement takes place through the means of the thermal conductivity of these particles. And if you would like to adjust the pH, then what we are doing is that, like, we are going to change the aggregation ability of the solution of these particles, and by increasing or decreasing the pH, and with respect to the base fluid, we would be able to create the surface ions, and also we would be able to neutralize some of the ions which are present, cations or anions present in the solution, and accordingly we'll be able to make these particles suspended for a long period of time. Precipitation means like it is going to get settled down, and sedimentation, precipitation, they are synonymous. And suspension means like they are going to be suspended. Like suspended means like it's going to hang without any rope or tie or anything, but it's going to hang with the help of your steric effects created by the surfactants, or by some other means. You will be able to make sure that the particles are not going to get attracted towards each other. And there are some applications which really requires the particles to come into close contact, thereby some thermophysical properties enhancements are made possible. And with respect to the concentration, as I have explained to you in the earlier slides, like volume concentration is a key parameter which you should be in a position to appreciate and use them appropriately, judiciously, when you are working on the nanofluids research. And temperature, again, it has its own role to play. So when you increase the temperature of the base fluid, its density is going to come down, and that the decrease in the density is going to create some kind of effect with respect to the particle-particle interaction with the base fluid. And this slide shows the classical thermal conductivity models being proposed by many researchers, and with respect to the shape, size, and then the phenomena with which these particles are going to behave in the base fluid. So starting from the Maxwell model, and then Hamilton-Crossan model, and then Brugmann model. So they all have dealt with the spherical particles. And what will happen if you dissolve or if you suspend a triangular nanoparticle or some other shape which is not belonging to spherical? So then we can actually look into the other models, conductivity models being proposed. So like Zuan, Ita, Ku, Klinster, and then Zhang and Choi. So they all have they gave some insights about when you add some non-spherical particles into the base fluid, how the thermal conductivity enhancement is going to take place. And there is a big doubt across the globe, like, is it really a fascinating thing that you are talking about, like enhancement of thermal conductivity, which is possible by adding nanoparticles into the base fluid? Is it really happening, or it's all like some kind of show which we are trying to do for the sake of producing papers? No, it's not. It's not like that. It's happening. It's for sure. Thermal conductivity enhancement happens. You can really enjoy this particular enhancement in thermal conductivity of your base fluid when you actually add these particles at very low volume concentration. Okay, keep this in mind. So do not supersaturate the solution so that you would feel like as if you have enhanced the thermal conductivity to a greater orders. No, as long as you keep the suspension of the nanoparticles at a lower concentration, yes, for sure you will be able to appreciate, or you'll be able to see that the thermal conductivity of the base fluid gets enhanced at a very higher proportions. And these are some of the other classical thermal conductivity models, developed models, which were inspired from the previously developed classical correlations. And Choi and Moshe, Hill, Feng, they have proposed the correlations with respect to the nanolayer effect, considering the nanolayer effect, and then the nanolayer thickness and the solid to liquid interface, capacitor resistance, and many other things have been taken care of into these models. So if you want to develop your own correlation, so I would recommend you to go through these correlations at first place to understand about the mechanism behind these correlations, how they have developed, and then you can do some kind of good experimental works, and you can always come up with your own proposed conductivity models. There is a lot of space available for you to develop it. And then aspects which are influencing the viscosity of nanofluids. So where is this viscosity comes into picture? So whenever you add any material, foreign material, into a pure liquid, fluid, so you are now going to increase the viscosity for sure, because you are now going to add many new ingredients into the base fluid, and you are now going to actually see that the viscosity of the base fluid increases to some extent. But to what extent this enhancement in the viscosity is going to keep your application working very well? That's the place where you need to do a good trade-off. Like as an engineer, you need to have a good balance between the viscosity enhancement and the thermal conductivity enhancement. In many literature, you would have seen like adding nanoparticles into the base fluid, it will enhance the thermal conductivity to 100% or 200% and all. But on the other side, there will be a penalty in terms of the flow properties of the fluid. Right. So again, the viscosity of nanofluids depends on surface charges, because as I said, with respect to the DLBO theory, and also the Stern layer, and as well as the double layer which is getting formed. So this is mainly because of the surface charges which these particles they possess. And then again into the concentration, how the Brownian effect is going to influence the concentration of your particles. So more the concentration, the thicker is going to be the solution, and again it's going to have high viscosity. And again, when you want to sonicate the particles into the base fluid, you will have to do at a particular intervals, and also from the loosely packed particles to the broken particles. So you have to take care of how to disperse the particles with some particular frequency. And also the surface density, that means the pH value alters the surface charge density, as well as the agglomeration of particles can be well adjusted with the pH values, and this is again going to add or reduce the viscosity of your nanofluid. And again, the temperature, I don't have to mention it in detail because of the known reasons behind it. And coming to the research works which we have performed on nanofluids in the recent times. So our team, under the supervision of Professor Kanai Selvam, so we have actually conducted a study on the copper titanium hybrid nanofluid. And we have conducted rigorous experimental work on the copper titanium hybrid nanofluids, wherein we have changed the volume concentration of the particles with respect to the base fluid. The base fluid which we have used was distilled water, and we have also examined the rheological characteristics of this fluid, and we have came up with some nice positions and also from nice conclusions out of this work. And in the recent time, we have our team, like along with Professor Deshmukh from BITS Pilani, we have done work on thermal conductivity prediction of titania water nanofluid, wherein we have used different machine learning algorithms such as the artificial neural network, decision tree algorithm, and many in that order. And we have done experimental work on the water titania nanofluid to predict like how the thermal conductivity enhancement would take place when the concentration of the nanoparticles are increased in the solution. And very recent work which was conducted in our lab is all about the thermal conductivity enhancement of magnetic nanofluids for energy applications, along with the collaboration of Professor Sridhar from our department, from chemical department. So this is the article which we have published in Experimental Thermal and Fluid Sciences in the year 2013. 2014 it was published online. I'm not showing this slide to promote our work, but still this work has got a lot of insights about the nanofluids, especially about the hybrid nanofluid. And if you are interested, you may please go through this work where we have discussed many things related to the physics and chemistry of the particles and their mechanisms, like the diffusivity, and then how the particles will have the interaction with the base fluid and all. So the purpose of showing this slide is that like this research work we have published in 2014, and till today it is receiving a lot of citations and it is receiving a lot of appreciation. So if you are interested, you may please go through this work at a later point of time. So I am going to now talk about some of the extracts taken from the work which is shown in this slide. So that's going to be the most important part of my today's talk. So this is the morphology of the copper titanium hybrid nanocomposites. So morphology means it talks about the size and the shape of the nanomaterials which we have synthesized, and we have used the field emission scanning electron microscope to visualize the particles, how they have been formed. And as you could see from the formation of these particles, so each particle, let's say, if you see, they are like some kind of flower kind of structure they have exhibited, and the particles are now they have got adsorbed onto the base substrate. That means the titanium particles, they have acted as the substrates for these copper nanoparticles to get them adsorbed onto their surface. So we have specifically designed and created this kind of a structure for our application. Why? Because there was a period where the saturation, it's our opinion, not a general opinion. So we have felt like, our team felt like there was some kind of saturation which had happened with respect to singular nanoparticle or nanofluid based research work. So we wanted to do something different, where that's the reason why we went with combining the metal and then oxide thing together to form a hybrid nanocomposite. And this hybrid nanocomposite particles, they have formed in this particular fashion, wherein the copper nanoparticles got absorbed onto the substrate of the or surface of the titanium nanoparticles. So this actually favored in terms of extended heat transfer like surfaces when they have been dispersed into the base fluid, because if you look at the surface arrangement here, so somewhere it looks like spikes and somewhere it looks like a pointed object. So the main intention of having this kind of structure is that to enhance the energy transfer between the particle and the base fluid. And this is the XRD pattern, which clearly shows like how the copper titanium particles, they are having their crystalline nature. So at 101 facet, and also at these phases like 200 and 004 and many other small peaks, you could see from this graph clearly indicates that the particles which we have synthesized, copper titanium hybrid nanocomposite particle, were highly crystalline in nature. So the main advantage of having added the copper into the titanium particle is that to enhance the crystallinity of these hybrid composites. Sir, can I take another 10 more minutes or 10 to 15 more minutes? Because I wanted to discuss something important here. Due to the time lag which had happened in the earlier session, earlier time. So can I have another 15 minutes?
Yes, sir.
Fine. So thank you. So this is the experimental system which we have developed in our lab. So where it is, it consists of a tube-in-tube heat exchanger, and it is well connected with both the hot and cold fluid reservoirs. And these reservoirs we call it as like nanofluid reservoirs. So we wanted to pump in the hot that fluid through the tube-in-tube heat exchanger to analyze the heat transfer performance of the heat exchanger and how the enhancement thermal conductivity is going to favor the heat transfer through the heat exchanger. And into the standardization of the experimental setup. So the very first thing what we need to do is that first we need to standardize our experimental setup with respect to the standard correlations developed for the water as a working fluid. So we have standardized our equipment with respect to the Dittus-Boulter correlation, wherein we have subjected the distilled water as the base medium to flow through the circuit, and we have seen that for different flow rates, how the Reynolds number and the Nusselt number to the Prandtl number ratio they have been varied with respect to the Dittus-Boulter correlation, and finally we have seen that we have got very marginal variation with respect to, or marginal deviation with respect to the standard correlation. So thereby we have first made the experimental setup standardized for our further research works. And this slide actually shows about the thermal conductivity enhancement of the copper titanium hybrid nanofluid. So in the x-axis you can see the hybrid nanocomposite volume concentration, which is varied in terms of the percentage of the hybrid nanocomposite particles, and at different temperatures we have observed like how the thermal conductivity of the hybrid nanofluid got enhanced. So yes, you could see from the graph, so it clearly shows like the enhancement in the thermal conductivity is for sure happening, and this is all because of the interference between the particle surface with respect to the molecules present in the base fluid. So the thermal conductivity enhancement happened very nicely at higher volume concentrations because more particles you are going to add and the more interfaces, thermal networks you are going to create in the base fluid. And we have limited our volume concentration up to 2%, starting from 0.1 onwards to 2 volume percentage, keeping in mind that the effect of aggregation will start pulling down the essential properties of the base fluid, and the particles at one point of time they settle down into the bottom of the tank. So we have used these standard correlations to predict the thermal conductivity of our material, and this is a graph which shows the experimental data plotted with respect to both the conventional correlations and the classical correlations. So as you could see from the figure, like the brown color cubes, so they stands for the the experimental values, and the other dotted lines, the curves, they show the values with respect to the standard correlations. So as we could see from the lower concentration onwards to the higher concentrations of the particle addition into the nanofluid. So at lower concentrations, these correlations could not well predict our experimental values, but at the higher concentrations, we can see that all the values are well predicted and they are in line with respect to the already existing standard correlations. Because those particles were not truly spherical in nature, but still we have assumed them to be spherical in nature, and then we have we actually got inspired from these standard correlations, and we have plugged in our values into those correlations, and we have checked that these correlations well predicted the performance of the hybrid nanofluid in terms of the effective thermal conductivity being generated. And with respect to the heat transfer coefficient, so you could see that the convective heat transfer coefficient of the hybrid nanofluid was enhanced with respect to different mass flow rates of the flowing fluid and with respect to different Reynolds number. So we could see that the gradual increment in the convective heat transfer coefficient had taken place, and even the overall heat transfer coefficient also has shown a good pattern of enhancement. These two things happened. Why? Because of again the the particulate diffusion which had happened when they are subjected into the base fluid. So the particles, nanoparticles with the high thermal conductivity, when they are introduced into the base fluid, so they will try to develop their own relationship with the adjacent fluid molecules, and through the phonon heat transfer, the phonons will exchange the energy, the heat energy within the particle, and from the particle to the fluid layer, again the phonon heat transfer, convective heat transfer takes place at nano levels. That's what we call it as nano convection effect. And Brownian motion to some extent, that means the Brownian motion of the molecules of the base fluid also favored to some extent in terms of enhancing the convective heat transfer coefficient of our hybrid nanofluid. And again, as I said, like we will always have some kind of penalty in terms of ending up with some power consumption when we subject the nanofluid to flow through the pump. So that is due to the development of both friction factor and as well as the pressure drop that occurs in the overall circuit, because the pump need to put some extra energy to push the fluid containing the particles, though it may not be that huge as we think, but still even a small, even an incremental increase in the pumping capacity also is now going to get influenced due to the addition of nanoparticles. So when you add an increase in nanoparticle concentration, it's again going to increase the pressure drop, and that's what, like as I said, like more particles are going to again going to occupy more volume, and again it's going to create more viscosity, and it's again going to impact in terms of the power being consumed by the pump. And when we compare our heat transfer effect with respect to the standard correlations, we could see that the standard correlations could not well predict our